So in this problem, we have to find the point on the given plane ax plus by plus cz equals to p, which is nearest to the origin. So let us first visualize this problem. So we have a plane ax plus by plus cz equals to p. Let us draw this plane. So we will draw the plane in the form of a parallelogram. So this is our plane, and equation of the plane is given ax plus by plus cz equals to p, right? So any point on the plane is x comma y comma z, because this will satisfy the equation of the plane, right? Now another information given is that the fixed point, and that fixed point is origin. So we are drawing we are plotting a rough diagram. That's why we are not using the coordinate system, right? And we have to find the point x, y, z on this plane such that it is nearest to the origin. So nearest to the origin means suppose I draw a line from here to here. So this distance, so this xyz point should be nearest to the origin. So nearest means this distance should be minimum, right? So this is a problem of maxima and minima, and it's a constant problem. This one will act as a constraint. So what is the function? Function will be the distance function, which is not directly given. So we start solving the problem. Solution. First we find the distance function using the distance formula. So distance between any arbitrary point x, y, z on the plane, and the fixed point origin will be square root of x coordinate minus x coordinate. It will be x minus 0 squared plus y minus 0 squared plus z minus 0 whole squared. And this comes out to be square root of x squared plus y squared plus z squared. Now this is the required function which we have to minimize, and our constraint is ax plus by plus cz equals to p. So this is our constraint. So we have to find the maxima and minima of this function d, subjected to the condition that the xyz points lie on this constraint, which is a plane. Now we know that to find the points of maxima and minima, we take the partial derivatives of the function as well as the constant. And finding partial derivatives of a square root function is a bit tedious. So what we do, we find a new function by squaring the distance function. So f function is equals to d squared, and d squared will be simply x squared plus y squared plus z squared, right? So the good thing is that all those points where the f function has a maximum value or a minimum value, at the very same points d will also, our original function will also have the maximum and the minimum value. So we will treat f as our function. So there is our equation number 1. So we have to maximize or minimize function f subjected to the condition, and the condition is given by this constraint. Now with the help of this constraint, we construct another function, and g function will be ax plus by plus cz minus p, and this one is minus p, and this is our equation number 2. So now our problem has simply become find the maxima minima of function f given by x squared plus y squared plus z squared subjected to the constraint ax plus by plus cz equals to p, and we will use Lagrange multiplier method. And what does this Lagrange multiplier method says? It says that gradient of function f is equals to lambda times the gradient of g, where now when we write this equation in component form, we simply get partial derivative of f with respect to x is equal to lambda times partial derivative of g with respect to x, similarly with respect to y and with respect to z. So this is our equation number 3, equation number 4, equation number 5. And we have 4 unknowns. The three variables x, y and z, and the unknown parameter lambda. That's why we need 4 equations. 3 equations are already there. The 4th equation we already know that will be the equation of the constraint. So we got ax plus by plus cz is equals to p, and this is our equation number 6. So with the help of these simultaneous 4 equations, we will find the points of maxima and minima. In fact, in this case, point of minima of this function d. So to apply these equations 3 and 4 and 5, we need partial derivative. So we find out the partial derivative. So partial derivative of f with respect to x is equals to 2x. Partial derivative with respect to y is 2y, and partial derivative with respect to z is 2z. Similarly, partial derivative of g with respect to x is a. Partial derivative with respect to y is b, and partial derivative of g with respect to z equals to c. Let us plug in all the partial derivatives into equation number 3, 4 and 5. So 3 becomes 2x is equals to lambda multiplied by a. 2y equals to lambda multiplied by b. The 5th equation gives us 2z equals to lambda multiplied by c. Now, contrary to what we did in the previous 3 examples, here we are, for a change, what we are doing, we are expressing x, y, z in terms of lambda. We will put those values of x, y, z in equation number 6. From there we will get the values of lambda, value of lambda, and as a byproduct we will get the x, y, z points, right? So from here we get x is equals to lambda over 2a. Similarly, y equals to lambda over 2a, and I beg your pardon, b, and this one is z equals to lambda over 2c. We put all these values into equation number 6. So we get a x value lambda over 2a plus b lambda over 2b plus c lambda over 2c is equals to p. We further simplify it, right? So it becomes lambda over 2 is common. We have a squared plus b squared plus c squared is equals to p. And we simply get lambda is equals to, 2p over a squared plus b squared plus c squared. So put the values of lambda here. We get from here, we get x is equals to, in place of lambda we will put 2p over a squared plus b squared plus c squared. 2 and 2 will cancel out, and we will simply get ap over a squared plus b squared plus c squared. And there's a symmetry in the problem. So similarly we get y equals to bp over a squared plus b squared plus c squared, and z equals to cp over a squared plus b squared plus c squared. So with the help of Lagrange multiplier method, we have obtained this point a, at which the given function f either has a maxima or a minima. Now, as we know that Lagrange multiplier method does not give us the nature of this point. It will not say whether it's a point of maxima or a minima. So we will use our mathematics knowledge to prove that, of course, this point, at this point a, f has a minimum value, right? So how to go about it? So the proposition is this: suppose we assume that f has a minimum value at this point. In fact, f has the minimum value at this point, because it will be an absolute minimum. So What does it mean? It means that at any other point x, y, z lying on the plane, the value of the function will be always greater than, and if it is a point of maxima, it means that at any its value of function f of the function f at this point will be always greater than the value of function at any random point, any other random point on the plane. Okay, so let us take a random point, right? Let us a random point on this plane, and the simplest one is, let us put a y coordinate and z coordinate as 0. So let us take x is equals to, say, p over a, right, and y equals to 0, z equals to 0. Clearly, if we put this point on the equation of the plane, so we will get a multiplied by p over a plus 0 plus 0, and this one will be equals to p, which is right hand side. So definitely this point satisfies the equation of the plane, right? Now let us find the value of function f at this point, right? So this will be x squared plus y squared plus z squared. It will be p over a whole squared plus 0 squared plus 0 squared. Value of f, say this point is, say, b, at b, right? And this one is equal to p squared by a squared. Now we will show that value of function at a is less than value of function at b, right? So let us calculate the value of the function at a. So f at a, we plug in the value of x, y, z into the function. So it will be a p over a squared plus b squared plus c squared whole squared plus bp, this is bp over a squared plus b squared plus c squared whole squared plus cp over a squared plus b squared plus c squared, and this entire whole squared, right? After simplification, we will get from a squared, b squared, c squared, p squared is common over there. A squared plus b squared plus c squared whole over a squared plus b squared plus c squared whole squared. Now this numerator of value of a squared plus b squared plus c squared cancel out one of the powers in the denominator, and we simply get p over a squared, p squared over a squared plus b squared plus c squared, right? So the value of function at point a is p squared over a squared plus b squared plus c squared. Let us first clear the clutter. So the value of the function at point a is p squared over a squared plus b squared plus c squared. Okay, next we will show that this fa value is less than the value of function at a random point b, right? So let us start proving this. We know that a squared plus b squared plus c squared is greater than a squared, right? So it's reciprocal. 1 over a squared plus b squared plus c squared will be less than 1 over a squared, and we are multiplying both the side of this inequality by a non-negative number. So p squared over a squared plus b squared plus c squared will be less than p squared over a squared, and this one is the value of f of a. Value of function at a is less than value of function at b. So value of function at the point A is less than a value of function at any random point of the plane. Okay, so it means it will be a point of minima. Okay, so we have proved that this function f has a minima at A, right? And it also means that the function d, which is a square root of f, also has a minima, right, at this point A. And what is d? D is the distance between this A point and the fixed point origin, right? It means this point where D is minimum is nearest to the origin. Fine. So FA is less than FB implies A is a point of minima of function f, and this implies A is point of minima of D function, and this implies A point is nearest to the A point is, this implies A point is nearest to the origin. So our answer is the point A with coordinates AP over A squared plus B squared plus C squared, BP over A squared plus B squared plus C squared, CP over A squared plus B squared plus C squared, which is lying on the plane, is nearest to the origin. Thank you.